Hi everyone, welcome. My name's John McFarlane and I'm going to be talking about contractual disappointment in C++. A little bit about me first. I work for Jaguar Land Rover in Shannon in County Clare in Ireland. Some of my code is available online in a GitHub repo. I'm on Twitter. And the slides, with only a few minor corrections, you should be able to see from here if you wanted to kind of check stuff, links. There's various, compiler explorer links, that kind of thing. If anybody wanted to jot that down quickly, I could wait, but otherwise, let's move on. Okay, so a little bit about what interests me. So at work, I've been a game developer. I've worked with back-end servers of various kinds, and currently I work in automotive. And in my spare time, I kind of noodle around with numerics. I have a numerics library. I'm really interested in workflow. I'd say kind of CI and tools, but just generally productivity, how to make things easier to do with software. I also dabble in word games, just as an excuse to code and solve problems. You could probably guess what word game I've been playing around with most. Any guesses? Wordle, very good, yes. All available on my GitHub. And in C++, in the committee, I'm kind of interested in low latency, so games, embedded systems, high frequency trading, that kind of thing. Numerics, again, and contracts as well. However, I should mention, if you're here to learn about the C++ contracts feature, I'm sorry, you might be a bit disappointed by my talk on disappointment. I talk about contracts a lot, including stuff pertinent to the C++ contracts feature, which was, it's been pulled from C++ 23 and was previously added to and then removed from C++ 20. I'm still hopeful that will be a thing. But I'm going to be talking more generally today about contracts. And it's not difficult to find a good definition of contracts. There were some good ones the other day in the no accept talk. But this one's as good as any. A contract is an exchange of promises between a client and a provider. The contract between you and your mobile phone provider isn't really any different to the contracts I'm going to be talking to today in relation to C++. Disappointment, though, where did I get that? Where did I choose that word from? Well, there was a paper from 2015 that talked about how to handle failure cases in functions, which is an interesting topic in C++ generally. And there are problems with using other terms. Sometimes they're quite loaded. These two in particular, very important, bugs and errors. And another paper there, the revision 2 of it in 2018, distinguishes between 3 different things, 2 of which I'm going to talk about today. So there's programming bugs, then abstract machine corruption, which is sort of Stack Overflow, heap exhaustion, running out of memory. I don't want to talk about what happens when abstract machine corruption happens because, it's a difficult and interesting topic. It's just easier if I just focus on bugs and then errors. And the important thing here is that they are distinct. You kind of might think of bugs as a kind of error, but there's a distinction here, and I'll show you how bugs are sometimes errors, but typically not. So a bit more about contracts. I'm going to focus on 3 types of contracts today. 4. There are four types of contracts I'm going to be talking about. So C++ API contracts are the ones you were maybe expecting to hear about. I'll certainly talk about those. Then the C++ standard itself is a kind of contract. Then there's what I call the end user contract. And finally, one which you may not have heard of or could even be sure you know what it means is the test user contract. That's something I've come up with to try and explain some of the confusion people have about contracts in C++. So all these contracts, really any contracts, have 4 attributes. There's some kind of agreement. I'm going to be quite vague about this in general, but a contract's not much use if it's not agreed upon by a client and a provider. That's the wording that Alistair uses in his definition there. And then the thing that's really interesting that people hone in on is what happens when the contract is broken, what happens when the contract is violated, and in particular, violation by the client, when the client breaks the contract. That's what I'm mostly going to be concentrating on. I'll talk a little bit about provider contract violation, but if I don't specify, I'm talking about client violation. It just focuses the discussion a bit. So here's the table of those 4 contracts against the 4 attributes there. And, well, I'm not going to say a lot about agreement. You might document the agreement somewhere. The document might be self-documentation in terms of asserts or good API design. And then the standard is a particular document. There are actually a number of standing documents related to the C++ standard, but that's the one people are generally talking about there. Violation is what happens when a contract is broken. That's the interesting bit, I suppose. And here now we see the distinction between bugs and errors there. The first 2, it's a bug to break that contract. And with the second 2, it's an error. And then this one is very interesting because when the contract is broken, well, the contract isn't really broken here in the same way as the others. Basically, a bug happened in one of those other 2, but in a special circumstance, we treated it as an error and not a bug. That's to come, but we really should start with talking about the end user contract, because the user is the most important kind of agent in any piece of software. It's very important to be very user-focused. Really, if the end user contract is broken, everything else is kind of in vain in a way. So this contract, the exchange of promises between the user and the developer of a software product, and I'll be somewhat vague about what I mean by a software product, because it could be a library, a program, an application, an operating system, who knows, but it's some kind of software. And we need to expect that a user's going to break the contract. It's kind of sort of fair that the user may do this. Because people make mistakes. Sometimes your user might not quite know how to use the software and may need to kind of play around with it. Sometimes to learn something, you try and break it, and that helps you understand the parameters of what you're dealing with. Also, though, there is the concern that some users may be acting maliciously, but we still kind of treat these as errors either way. And these errors need to be handled. They've got to be handled by the program. Okay, so a bit more about errors. I'm just basically going to labor the point that the kind of errors are messiness. They're unpredictability, unreliability. Humans are a huge source of errors. Humans are squishy, messy, erroneous things. They're not very precise. And so the input that a user provides to the software is likely to be a source of errors. Command lines, network traffic files, input devices, configuration files, they would count as files, even if they're considered part of the software. Although some of these definitions can there's exceptions to a lot of this stuff that I'm kind of brushing over. The real world, the boundary between the real, sort of the program and everything sort of outside the program is sort of where you need to be sort of vigilant, I suppose. A file system and string are two just examples from the standard library of UI elements. What is string a UI element? I would argue it is. File system, you're still maybe thinking, oh, that's a computer thing, right? That's not a that's for transferring bits of data around between programs. Is that really a UI? Well, consider what would happen if Skynet took over and was now in charge of the C++ standard. Skynet would probably deprecate file system and string, I would say. And then Chrono, that's not so much user input, but it's real world. It's messy. And one way to think of this very sort of loose kind of comparison here, but there's messy, squishy stuff going on in the real world, and then there's kind of this there's sort of purity in the software itself, and so yeah, we're really looking at to begin with the errors, the messy stuff. So yeah, your program might be perfect, but errors can still occur at runtime. So some examples. I only came up with two real categories of examples. There may be only really one, and I'm thinking maybe I'm quite blinkered here, and I need to get a broader range of experiences. So please, if you have any suggestions for other types of errors, please let me know here. But I sort of think of resources being a source of errors. So if a file is needed and it's missing, or you want to write to it and you don't have permission to, there's somebody hasn't plugged something into the system that needs to be there for the software to work. Maybe a resource is tied up already, and just in general, if you're dealing with an API, particularly a system API, and it's got a return code, and you maybe didn't ever bother to check that return code. I mean, I've never failed to do that, but one or two of you may have. That's often, if you dig into what those error codes mean, you're looking at errors quite often, hopefully most of the time. And ill-formed input, well, that's really, we're talking still about resources, aren't we? But in particular, you might have got the input, but the input's wrong in some way. The file's too short. It's just not well formed in the format it's meant to be in. There's a parameter that needs to be within a certain range, et cetera, et cetera. So how do you handle errors? That's the million-dollar question, really. It's just to remind us, it's a client violation of the end-user contract that needs to be handled by the program. I'm not talking about if the provider of the program violates the contract. That's bad. We'll get on to that. We're talking about client violation here. And really, what purpose are we serving here? We want the user to know that they did something wrong. It's pretty much all up to the user. The user wants to plug that device in, change the permissions on the file. If the user can't do that, then you're pretty much stuck. But certainly the program can't do it. And so the purpose of all of this is you're communicating to the user. You're trying to help them. And so it's good to think, well, what if I was the user? Very often you are the user of your program. But what if I was the user and I had no clue about this software? How can I be helpful to the user when issuing errors? So yeah, how do we do that? Really, really depends, unfortunately. Depends on a lot of things. This isn't talked about a lot, but there's kind of, I think, software coming in sort of two varieties there: batch programs and steady state programs. A batch program is you think of a typical Unix command line parameter program that you run it. You maybe pass some parameters in. It maybe reads some files. It does some work. When it's done with the work, it outputs the results and it finishes. And if you're writing a program like that, it's really nice. There's some constraints to that that make things very easy. If your program's steady state, a web server, a game, software on a microcontroller, perhaps, then your program's ticking over. It may not be clear when the program's going to end, and if things go wrong while the program's running, you can't just sort of return back with an error status every time somebody asks for a web page that isn't on your file system. Real-time constraints can have all sorts of effects on error handling. And how are you actually communicating to the user of the program through the terminal, through a graphical user interface? Is it a RESTful API? Is it something else? It could be all sorts of other things, or it could be nothing at all. You might be working on a system that doesn't even have a little red LED to blink. How do you communicate errors then? I certainly don't have time to go through the answers to all of this. Worse, your program, it might not even be a program. The software you're developing might just be a library, and your library might end up being used in all of the above. Now what do you do? It's pretty tricky. There's many choices, and there is a problem with C++ having too many error handling facilities, and there's some great talks on how there are way too many of them. But part of that is because C++, as in the last slide, there's a lot of things you can do with C++, and so that is part of the problem. There are just some problems that deciding on one solution just wouldn't solve. But versatility, I'll come back to that later. Versatility is important, particularly in that last example. But I'll concentrate on the really simple situation where you have a batch program, okay? And here's the header to your wonderful program. You're very lucky if this is how your header looks. You have some kind of input, and it is error-free. Okay, that's the thing you might pass into a unit test, for instance, if you were testing your code. Okay, and then you have input from the command line here. Args is a sequence of command line parameters passed into digest input, maybe digest input. It parses those command line parameters. It maybe loads some files, some configuration files or files mentioned in the arguments. It does some work to translate that into input in the way that your program really wants it, or it fails. It maybe detects an error. Something goes wrong, that file's missing, et cetera, and so it doesn't return input at all, hence the stood optional there. That's kind of a placeholder for, just to make it clear that you maybe get a standardized input back from this, or you maybe don't. And then once you have the standardized input, again, if you're really lucky, then you just have the function, the code that does all the work. And if you're really lucky, or if you're maybe working in a safety critical application where you have really strict constraints on things that you can do, you might not even be allocating memory dynamically in here. Typically you will though, but you maybe don't ever have to account for an exception getting thrown in here, or just any kind of error happening. And then maybe it prints, maybe the output is a string. And then your main function sort of looks like this. Most importantly, and we'll get to this, preventing problems is always better than having to deal with them at runtime, and that should be the strength of any strongly typed language. Here, for example, we have two variables that are kind of closely bound to one another, and we group them together into one object. It makes it much harder for an error to occur later on. We're just using type safety to help us avoid problems. Then we take this input. We try and digest it, and if we fail, we'll just exit. Perhaps inside digest input there is some helpful diagnostics for the user, but the control flow is that we now exit. If all was good, then we just do whatever the thing is, and the code inside there is probably way cleaner than if you tried to mix the error handling and the sanitizing of your input, along with the actual processing of the data, you tend to get messier code. It's often less efficient, and it's certainly harder to maintain, understand, and write. So, some techniques. Now, there's really two things going on with error handling. There's the actual reporting. So you might print a standard error. That's the simplest case. And then there's the control flow, what we call the SAD path. When things go wrong, you need to redirect program control with maybe exceptions, return values, or basically aborting the program. And there are, and again, this is typically in a batch program. These are very likely choices. If your program has to continue past errors, then you sort of have to deal with ways to report things back to the user or the client, and still manage to continue afterwards. So let's look at let's go really low level and basic here, and look at some kind of strategies. So here we've got a function. It's not very useful. It prints a file size, and it's often handy to know what the size of a file is, but printing it to the terminal isn't particularly useful. But it's just our first example here. We're returning true or false for success. Was the function successful? True if it was, false if it wasn't. And again, there's a load of other things that could be going wrong here that I'm sort of brushing over for the purposes of brevity. But let's just say the file wasn't opened for whatever reason. That's the failure case. And then we print, we log details, standard error. That's the thing that we hope that perhaps the user will go, oh, okay, yes, that file's not there. I maybe provided the wrong file name on the command line. Now, where that function's used, you might have more context. In the calling function, it's not just a file, it was a configuration file. So now you've got a slightly better information to give to the user. And the better the quality of that information, the more helpful you're being. Again, it's all about sort of being considerate to your user. So, not great, because really we want to return the file size. But now we have the problem, how do we return success? We're still logging, sure, but so now we're going to return the result or the failure using std optional again. And there are other components available other than std optional that might be a better choice, but this kind of gets the job done. Either we return the result or we return failure and log the details. And so, so here we're getting around the basic problem that a C++ function cannot return more than one thing, even if structured binding is really returning one thing and then breaking that up. Now, this is, I think, a perfectly reasonable way to report an error in a simple program. If it's okay to do this, then do this. And if you're worried that you didn't free up some file handles or dynamic memory, that's not a reason to worry that you're not quitting main in a clean way and that you're bypassing destructors. Be aware that you are not calling a whole bunch of destructors potentially, but your process, if it's on a modern operating system using sensibly designed resources, this should not be a problem, and you fail fast. Failing fast is an important, well, it's a valuable property of a system. If you're going to fail, just hurry up and fail. Okay. And here now we're returning the result from the program. Exit failure is the standard code for this program's failing. And a lot of what I'm talking about here today, it's not just about functions or C++, but software in general. So what goes for reporting an error condition back from a function goes for reporting it back from a program as well. And here this is just a point where we decided we expect 3 parameters, and there's only, there are more or fewer parameters, so we're just going to bomb out. And that's, you know, in a simple program, this is okay. This is okay to do. There's our details being logged there, passed into Fatal. And do we have any questions so far? I should have said, please do feel free to ask questions now, or can you see the number there? Is it just about visible? Some of you might not be able to. I don't know, but yeah, if you have a question and it's about a particular slide, I have slide numbers there. Okay. So functions are a track event. Can anybody guess what I mean by a track event? Athletics, yes. A track event is kind of the runny events at the Olympics or the Commonwealth Games or whatever. And they typically they involve running a distance. Sometimes they involve jumping over things as well. But at the end of the distance, you're typically running through a bit of ribbon. You've got to the finish line, and unless it's a really confusing track event I've never seen, there's only one finish line, but there are 0 or more obstacles typically. And so this is how I typically lay out a function that might have to deal with disappointment, with errors. You know, at some point maybe there's some input, and from the input I need to get an intermediate object. There's some work going on, and it might fail. If it fails, I'm going to early out. I'm going to quit the function early with whatever the failure code is there, and otherwise I'm just going to keep working through the function, getting through these overcoming these different hurdles. And at the end, if nothing went wrong, if I didn't trip up at all, I make it to the finish line. Now, if anybody remembers Guy Davidson's keynote on Wednesday, a long time ago, he was reviewing some code which involved a lot of nested ifs. And the first thing he did was flatten down the structure of the function. It maybe got a bit longer, but there was less white space on to the left of the code. And generally, I think this is just less cognitive load on the user. You're reading this bit of code, you're thinking, okay, what's going on here? Is this going to pass? Is this going to fail? Once you've got past line 6, it's kind of out of sight, out of mind. You don't have to worry about all of that stuff. You now know you've got your intermediate thing 1, and you can just concentrate on the rest of the code. This is, for my money, the best way to sort of lay out a function with 0 or more failures. At the end, the good thing's going to happen, basically, whether there was with no failures or many. And exceptions. I'm not going to talk about exceptions really. I could go on at length about them, but basically they've got a lot of pros and a lot of cons, and depending on who you talk to, the pros and the cons are the same. They're efficient, they're inefficient. They hide away the control flow for when errors happen, which might be good, might be bad. It's really to an extent a matter of opinion. But that's all I'm going to talk about. End user contract failure. It's really what we're generally talking about when we're talking about errors. Next, the C++ API contracts. The thing that we actually think we're talking about when we talk about C++ contracts. APIs, and they're the things that can go wrong there. Now, again, exchange of promises. Between developers, often the same developer is writing the function and then calling it, or the class, or the type. We'll generally talk about functions. I think that's where we sort of concentrate notions of C++ API contracts. When they're broken by either the provider or the client, those violations are bugs. End of. No, there's no more conversation to be had there as far as I'm concerned. And bugs need to be fixed. And things start to get a little contentious as we talk about the situation where a program has bugs in it. But a program with a bug it's not correct. Okay, it has undefined behavior. Doesn't matter what kind of bug it is. If there's a bug, you don't have full control of your program anymore. You've kind of, the steering wheel has come off in your hand, so to speak. The program can be assumed to be vulnerable to malicious attack, or it could have some kind of safety concern there. And also there are knock-ons here. The violation of the API contract consequently means that the end user contract is violated here. And this is all very absolutist. I understand that, but it's a good place to start from, is sort of just facing up to the fact that once you've got a bug, bad stuff happens as a consequence. And we're now talking about the stuff on the right. We're talking about the software, mathematics, as opposed to the squishy stuff. Okay, so I'll talk about a PID controller. This is quite a nice example of an API contract that's very clearly just a bug within the API rather than anything else. A PID controller, it's a sort of type of a controller for controlling systems, often it's maybe mechanical systems, regulating something, controlling a value and trying to keep it to a certain a target value. You might find that a heating system perhaps has a PID controller, or the auto cruise on a vehicle might involve a PID controller to regulate the speed of the vehicle, for instance. And if you look at it's essentially sort of a formula, if you like, a system where you have a variable. Here in blue, we have a set point. So the process variable, it starts off at 30, but we want it to be 10. We want that value to be 10. We can't set the value. It's just a property of the system, but we can kind of influence it by applying like a correction. So maybe like acceleration or turning on the boiler in your central heating system. And so the red line is the correction that we need to apply. Here to begin with process variable, it's 30. We want it to be 10. Therefore, we really want to apply a negative correction to it. Hence red being below the line there. Now, if P, I, and D are parameters of this system that can be adjusted, and here we see if we negate P, the system is really not controlling the variable like we want it to. It's kind of interesting. It's still plottable, but it's maybe fair to say that this is a violation of a contract. And there's some evidence of it. If we look further down the Wikipedia page, there is, I've not scrutinized this whole passage for contracts, but can anybody see the offending contract in this section of code? It's fairly early on, and I'll put you out of your misery. It's just that non-negative. It has to be the P, I, and D have to be non-negative. And this page isn't going to say what happens when they aren't non-negative. You can maybe guess if your kettle is trying to boil some water and it's using this, things are not going to go well. You don't really need to know what's going to happen to know it's a contract. So I thought I hunted down somebody's gist on GitHub, and they'd written a PID controller that was wrapped in a pimple interface, and I thought I can make this a lot simpler by using fewer abstractions, but maybe the right ones. And so I came up with just a model where we have there's three terms that are applied, but these components aren't necessarily the terms, and so it's important to know exactly where the contract sits. There are components, P, I, and D, in this model, but then there's there's constants, of which there are 3, that are passed into the system. So it's specifically K here, in which the contract applies. The components of K cannot be negative. Then we have a time delta as well, which really probably want to keep constant. And then there's some variables that are fed, that are produced by the function and fed back in on the next iteration there. And then the input to each iteration is the set point which was 10 in the example, and the process variable that started at 30. That's the one that's kind of, we don't have direct control on it, but we want to influence it, and we want it to be as close to set point as possible. And the result of the function, we get the correction, the amount of kind of influence to apply into the system to try and regulate that value, and then state those variables that keep getting fed in each time are there as well as part of the result. And then there's the signature of the function. This is all within the PID namespace. So we take the parameters, and by this I don't mean C++ function parameters, I mean system parameters, the things that describe this particular PID controller and that don't change from one iteration to the next. The state, just those variables that circle around, and then the input, because the actual process variable can vary every single time, and you might change your mind if this is part of an auto cruise system. You might want to change the speed at which you want to travel at any particular time. And then here is the definition of the function, and here is where we express that contract from the Wikipedia page. And this is pretty. If you're able to express the contract programmatically, this is kind of how you do it, with an assert that's as simple as that, I suppose. Now, if there was a language feature, you might be able to express the same information, perhaps in the header file for this function, or in some other way. But it amounts to the same thing. You're just sort of saying, this must be true. These things must be true for the contract of this API to be upheld. I threw this one in as well. I don't think it's going to help if we try traveling back in time. And there could be many other things that could go wrong. Parts of the contract, elements of the contract of this particular API that I'm brushing over. This isn't the complete, just because you satisfy these 4 assertions doesn't mean that everything's going to go well. But if you violate any of these 4 assertions, just assume that the very worst can happen. Okay, so then there's some sort of intermediate variables there. Observe the constantness as a lot of sort of features, new and old, are helping me to avoid messing things up there, particularly like the designated initializers here. This is the first time I've used these, and when you've got a bunch of variables, they're all the same type, you could mix these up. And indeed, the example I took from the internet had P, D, and I as the parameters, and a few times I kind of, my graph started going wrong because I'd mix those around. Much harder to do with these designated initializers. Thank you, C, for coming up with those, and I'm very glad they're in C++ as of C++20. And then these terms, the PID terms, are added together at the end and output. Now I mentioned, so here I'm using the components object again. It has these 3 variables, but these are not the constants, the parameters, the K values. They are products produced from them, and they can be negative. So I was mentioning earlier, components is not where the non-positive stipulation was. It's actually in the K values themselves. So if we go up here, there we go, there's the Ks. Okay, yeah, we output. Now we form that into, actually I probably could have used designated initializers there as well, but yeah, that's so a very simple example with no classes. I could have used templates, but I stuck with double, and that's just a very simple example of a contract that has been basically provided as part of the API. Somebody wrote an API. So this is another example. This is like a real-world example from a previous company I can't name, which I'm not going to anyway, where they had a UID for which identified items which are very important to this company. And sometimes they had a value of -1, and yes, this is an unsigned int. It's kind of okay, it's considered okay for legacy reasons that you can assign -1 to a uint, and you kind of get all your bits set that way. This is a sentinel value. Basically, this type is representing an item or kind of not an item. And elsewhere in the program, there's this helpful kind of bit set class, and it stores a Boolean value for every single item in the system, and they tend to be numbered sequentially. So this thing just used a huge array or vector of I don't know if it was vector of bool. I can't remember. I'm pretty sure it wasn't. But yes, it just basically had a bit reserved for each element. And here there's a getter. So given a particular index into this container, is the bit set true or false? And helpfully, I'm going to emphasize and kind of quote that word helpfully. If the index was out of range, actually yes. I mean, capacity, size, they kind of mean one and the same thing here. I probably should have said size, but yes, if the index is kind of out of range, resize the container with the any new values being false, and then just return that value. And I don't even write down, I can't remember where the exact bug happened, but you could probably guess that somewhere the Sentinel ID wasn't checked, and a value of 4,300,000,000 odd was entered into the system as an element, and the servers in this system were big enough that it allocated 4 billion bits worth of data quite happily, and just weirdness happened, which took somebody best part of a weekend to figure out, because this was on a business critical system. And there's a few things to say about this particular bug. I'm not really talking about. I mean, I've not identified the contract specifically, but maybe asserting inside get that index is not the Sentinel. Well, we couldn't really do that because bitset is not specific to the UID, but maybe where we call get, we might have wanted to assert there. You sure this isn't the invalid value? Sentinel values are trouble, and that UID, that type def could have been replaced with a class that made it harder to confuse the Sentinel value with a valid value. And defensive and helpful code is I'm not a big fan of it, I've got to say. If you add extra code to try and fix things rather than just fail, you're usually just making things worse. I should say, I'm not sure it comes up in any other slides. I know, I've been to a few talks today, this week, great talks about dealing with errors and bugs in code. And there was somebody working on a piece of software where a lot of, a file might not be available on the system, and it might be okay that the file isn't there, that the program might continue. It might be a configuration. If there's no configuration file, there's a default configuration, and it's fine. It's no bother that there's no configuration. That's not an error. That's just a condition of the system, and that's fine. But generally, if something is wrong, better to just fail than try and patch it up in some way. I've got some terrible stories about time wasted because something went wrong. there was some kind of measure put in to try and helpfully work around the problem, and then a long, long, long way away, elsewhere in the code, there was a bad consequence as a result of that. And it's just really hard then to go, well, where did this go wrong? It could be anywhere now. I don't see the error in front of me, and you have to start spelunking through the system to figure out what went wrong because somebody was trying to be helpful. Don't be helpful, okay? And yes, trapping things early. That's really what I'm talking about here, rather than kind of brushing things under the carpet. So that's all I'm going to talk about C++ API contracts for now. The standard is also kind of a contract, or maybe multiple contracts. There's, as I say, one or more documents related to the standard, so it's well recorded. Yeah, as a standard, it's sort of kind of an exchange between promises between C++ developers and C++ implementers, as authored by well, the authors of the contract, typically the C++ Standardization Committee. And again, lots of ambiguity between these three different parties here. They're often the one person. There'll be somebody, they go to the committee, they help author the standard, then they implement it, and then they use the implementation. Or it could be three separate people, very often it is. And again, client violations are bugs. Provider violations are bugs as well. If you hit an actual genuine compiler error, that definitely is a bug too. In fact, yes, that's then a user contract violation. Yes, violation is a bug, and violations are undefined behavior. And then this is the UB that people often think of when they talk about UB. They're talking about the things in the C++ contract where either it's explicitly stated that a certain consequence is undefined behavior, or it has been left undefined in the standard and then implicitly is, well, it's clearly not undefined. So again, I sort of think of two categories of bugs. And when I say prominent, I mean these show up in bug reports, exploits, vulnerabilities, that kind of thing. So integer arithmetic, particularly signed integer, there's divide by zero and overflow are two things that can happen with integers. I can't think of any others. I ought to really know if there are others, but it kind of comes down to that really. And then object lifetime is it's tough in a language with no garbage collector. You might have a null pointer to begin with. I don't know if object lifetime is quite the right term, but stuff to do with lifetimes and pointers and references. Like you've freed an object, and then you still have a reference to it that you use, or you go out of bounds related to numeric errors, but really the error is when you try and look up something that's outside the sequence. Or you might double delete something. There's also leaks, not really a bug. As I mentioned earlier, you could have allocated a load of memory and then you call stood abort because something bad went wrong. And yeah, you've leaked the memory, but I don't think that's considered undefined behavior by the standard. But a lot of people would consider it not good if you're leaking memory. And in the general case, yes, try not to leak memory. Now, two of these, the top two, divide by zero and null pointer dereference, I think are kind of special. They, I think they attract less ire and they probably cause less problems than the others. Can anybody think why those two would seem to be less of a problem to people? Is there something about those two that you tend to find is it makes them less worrisome? Well, on a typical PC, these two, if they happen, the program will crash. Basically, they are trapped by the system, and that happens to People, they complain that the program has crashed, but they don't complain that a program crashes because you try to dereference the null pointer. So the fact that they are undefined behavior in the standard, I think bothers less people because, they are users, we're users, and being told when something's going wrong, actually, you don't feel so bad about it than if you release code to a user, didn't know about some kind of rule in a standard, and then find out a year later, you made a bug, it's your fault that you let your user down. I think that causes a lot of anger and surprise amongst developers. More on that later. So here's a program with the bug in. Now really, what line do you think that the bug is on? 3, yes. Hopefully, I just making sure I can get some feedback from the audience there. And here, look, so again, letting people know that something is going wrong is a good thing. And the sooner you let somebody know that something's going wrong, the better. Just because this is a runtime behavior, and look, the program failed line 130, error code, exit code 132 there. That's basically saying this program failed badly. But before that, the compiler has said, things are going to go badly. I'm going to compile this because you asked me to, but I don't think you're going to like the result. And that's about shifting left. Shifting left means finding out about problems sooner, earlier on in the cycle. If you imagine you start coding on the left and you release your software to your user on the right, you want to find out about problems as early on as possible. The cost of finding out about a bug that's been released is huge. The cost of the compiler saying, oh, you made a mistake here, tiny. Certainly, if the bug escapes off the far right, that's kind of the failure that this talk is all about avoiding, really. So yeah, intercept your bugs early. You can make APIs. There's something called the pit of success, but a lot of APIs, a lot of standard library constructs, language features are designed to make it just impossible to even think about the bug. And then you have many tools to help you find bugs earlier. And it's great if the compiler can tell you about a bug, but not all bugs is it possible to say for certain a program will exhibit until you actually run it, and that is a problem. But what do? You instrument the code so it will find that error. And then you test the code. You put the code through its paces. You run automated tests so that when that bug does happen, you're told about it, you now know you've got a bug, you can fix it. And then to help you write those tests, fuzz test, or measure the code coverage of your tests, you can find out which bits of the code, which bits of the behavior you're not testing for yet, and then you can add the test, and great. And you keep running that test early and often. So here's some flags that will help you. I'm not going to go through all of them now, and sorry if they're a bit difficult to read. There's a link there to the document that I've written, which basically there's a document version of this talk. These are some flags that I've been collecting that are useful in dealing with contract violation in C++. The top 5 are really just about asking the compiler for help, asking the compiler to tell you about more things that might be wrong, and to be really insistent that no, you've got to fix these before the compiler is even going to produce an executable for you. But then there are many of these are related to bugs and contract failures at runtime. More on that later. This is a great example that came up in a talk the other day about teaching, and I guess a student had run this code. There's a bug in here, and it wasn't caught by UB sanitizer because, so what's going on here? So we're adding 2 numbers to a vector. Well, we're initializing a vector with 2 numbers. We're pushing back a third and then we're trying to dereference the fourth element. So that's out of bounds. However, pushback reserves some extra space for future growth. And so that pushback on line 4 probably increases the capacity of the vector from 2 elements to 4. Now, one of those is unused yet, the one at index 3 there, but there is memory allocated for it. And so sorry, not UBSAN, ASAN, the address sanitizer, doesn't immediately notice that that's a bug because no sort of what are sometimes called language UB violations have occurred. And yes, the speaker was saying this didn't cause an obvious problem, even though the tools were turned on that are meant to tell you about this stuff. However, there are still other things you can enable. They're in that list I just showed you, and this one in particular, it just basically turns on assertions in the standard library implementation. This is the GNU standard library implementation, but Clang has one as well, and Clang also has a macro like this that you can turn on, and the standard library will try and help you. This is obviously a bug, and it's easy to write an assert that will fail when this bug happens. I think this is the equivalent Microsoft macro, but I didn't test it. But this adds a load of checks to your program to try and catch bugs. So while you're testing, it's highly recommended. Whilst I was, I should probably check how I'm doing for time. Got about an hour left. I think I'm on track. Yes, so there's the program there. I've added it to the repo that I mentioned earlier. But how do you test a contract violation? It's kind of tricky. Usually you do something called, you write something called a def test. And what that basically does is make sure that the program crashes or fails or quits with a non-zero exit. The problem is, when this particular assert fires, I guess abort gets called, and abort crashes the program so badly that even the test framework kind of bails out as well. So I'm using C-test, and C-test was coming back with, I wrote a test that said, make sure that this program, I want it to fail. I don't want it to succeed, I want it to fail. And C-test was just sobbing and in a heap, and just going, well, this thing aborted, and I can't continue. It didn't return exit value 1 or 0. It was like 130 something. And a quick Google suggested you need to change the abort handler and just make it exit with the failure code, and then the crash isn't quite so violent, if you like, and this test will sort of gracefully, a bit more gracefully fail. And while setting the error handler, one of my warnings or static analyzer checks that I turned on said, "Hey, you've not this system function returns an error code. You need to check your error codes." I went, well, fair enough. I did just write a whole section of a talk on error codes. I probably should now add an error code here into some code where I'm testing for bugs. And then the question arose, well, what happens now if this API fails? I'm not expecting it to, but I should at least do something. I maybe should have printed out some helpful diagnostic here, but I figured, well, I now know that abort will make sure that the test fails regardless of whether the death that I'm testing for has happened or not. So, yeah, that's how I wrote that little bit of hacky code there just to test that those 3 lines from the previous slide do what I was expecting them to. Death tests are difficult, and you'd be forgiven for not necessarily testing every last. In fact, generally don't try and test that your asserts are doing what they're meant to. They're kind of outside the scope of the program, the correctness of the program. They're sort of beyond that in a way that you can't really test very easily. So, okay, that's it. That's for the standard contracts. And now finally, the test user contract is a made-up contract. I made this up, and some of the specifics of it I'm not quite sure I've got right yet. But it's basically a weird cross between these two contracts that result in bugs and the end-user contract. So basically, our compiler is a program that somebody wrote, and as a developer, when we use it, we kind of got two hats on. We're the user of some software that we're using to develop some other software, and so sometimes you're using those tools to test the software, and that's where the test user contract comes in. And it's worth knowing about, because I think it causes a lot of confusion and a lot of people talking past each other when they're trying to establish what they mean by a contract in C++. So again, an exchange of promises between the C++ developers and C++ tools providers. Very often, that'll be the developers who implemented your toolchain. For instance, if you have a sanitizer which traps bugs, the people who made the compiler are also bundling the sanitizer along with it and providing it to you. And it's kind of optional. You're not breaking the C++ contract if you don't provide these tools. And so, speaking as somebody who's works with embedded developers in safety-critical applications, sometimes they will find themselves working with some, frankly, quite low-quality tools, poor compilers that don't do a very good job and don't come with many of these nice-to-have extras, which is a bit of a shame, because in a safety-critical setting, you would like to have tools available to you that are designed to improve correctness and therefore safety. So it's kind of a shame that that is the case. And now, so contract violations, they happen in the same place as the bugs we've been talking about, but now they are no longer bugs, they are errors. And they arise at the point where a bug is discovered. So we were looking at some asserts earlier. At the point where the PID controller observes that the input was wrong, there's an assert there, and the program would fail, and that's a bug. But now, the same place, that's going to be an error. And now the user is the developer, who is the one now that we care about giving that helpful, useful information to. And asserts themselves are one of the tools that that can be provided. So sometimes you're a developer of a C++ API, and this is where I still haven't really cleared this up entirely, but you're now providing, you're writing assertions in your APIs to help the user of your code. And in certain circumstances, when the test user contract is being used, those aren't bugs anymore, they're errors. Okay, so now I'm going to talk a bit about, so I showed you the PID controller, and I used a macro PID assert. Sorry for using a macro. It's not a good thing to do, but somewhat helpful in terms of reporting errors here. So I have a case where if I'm testing for code coverage, I'm not interested in assertions. They're not really the stuff I'm trying to test for, so I discount the asserts. If the ndebug flag is not set, this is a flag that basically, it's like you signing off on a bit of liability there. If you define ndebug, you're saying, okay, please don't trap bugs that were identified with the assert macro from the cassert header. But generally, that's sort of, I think of that as meaning, okay, we're going to sort of, we're going past the point where we very explicitly want to be told that there's a bug. So if that macro is not defined, the assert, it tests the condition there, and if the condition fails, then we're going to call terminate. Stud abort actually might be a better choice here, but stud terminate is not so bad. Stud exit as well is another possibility. And this is a very simple implementation where we're just going to say, the program's going to fail, okay? It's going to exit with non-zero status. Any C test or whatever your test framework is going to say, no, that test's failing if you're expecting the program to exit nicely. You could maybe also put some diagnostic information here that might help, but really you probably want to be aware of how to run a debugger or take a look at a stack trace when crashes happen anyway. And so now this is where it gets a bit contentious. If I'm building for GCC or Clang, now if the condition fails, I'm going to say built-in unreachable. And just to remind you, ndebug is defined at this point. So normally a normal standard assert would not do anything at all. Here I'm saying, okay, if we want to turn off asserts, then we need to be absolutely certain that there are no bugs in the program. And this, we're basically saying here in the language that the tool chain understands, this cannot happen. This must not happen. That's what unreachable means. It doesn't mean make my program go faster. It doesn't mean add bugs to my program. It means this line cannot be reached. This expression here, it will not, it cannot, it must not be reached. And there's a similar way to do that in MSVC, and in, I think, C++23, there's stood unreachable. I think maybe the C standard is also standardizing this, so that this definition will be cleared up a little bit. And at this point, some people are already going, no, this is a terrible idea. But bear with me. I get why this should make you nervous. Right, so how you handle bugs. As I mentioned, you might be writing a library, and all sorts of people, game developers, people writing Mars landers, could all be using your code. You don't know what their needs are. We'll go into that a little bit later on. But there's this idea that, okay, so there's some undefined behavior in the standard which is there for maybe unfortunate reasons or complicated reasons that aren't really about bugs. But a lot of the UB that people talk about in the standard is, it means that you're looking at a bug, and it's clear that there's a bug there. And bugs are not good. A lot of software has bugs in. We'll get to that. But if you're not sure whether your code is correct yet, you really should be unsure. That's not, you should be sure. You should be unsure that your code is as great as you think it is. You're taking a risk when you release it to your user. You're also taking a risk if you optimize your code. And that has always been the case. It is becoming more so as compilers get better at optimizing code. It means code with bugs in has more problems associated with it. And really people try and compartmentalize different bugs or UB into different categories that are maybe more or less safe. And I think that it's a mistake to do that. I think you really just have to stick with the idea that all bugs stink, and you're in trouble regardless of whether you optimize your code or how you define that macro. As soon as you've got a bug, your program has undefined behavior. Doesn't matter within which contract it's made clear that the behavior is undefined, you're already in trouble. And just to illustrate that, here is an example of an API, a simple API that takes letters from A to Z. Well, it takes a number from 1 to 26 and returns a letter, capital A to capital Z in alphabetical. I'm pretty sure there's guaranteed alphabetical order. And there's, I don't know if I didn't stipulate, it's not highlighted, but there's a precondition in the comment there. The number is in the range 1 to 26. That is a contract there, okay? And you might think, okay, this is an example of API UB. This isn't standard UB. This is the OK UB that we're not so afraid of, that can't go that can't go wrong. There's going to be no time travel as a result of this. This is just UB that this just somebody coding like normal. Everything's good and dandy. But there are cases for which you now, as a result of how this function is implemented, there is language bad UB, language UB. There's a different kind of UB that somehow is considered worse. Really that's kind of missing the point of what contracts are about. They are about making it clear the safe parameters within which you can use the function. And why would you want to do that? Well, obviously to avoid bad things happening, but also the provider of a contract, particularly if the provider is going to provide this contract for many different systems and across many releases of their software, they need to reserve the right to change the implementation. Now let's change the implementation of number to letter here. Now we're using a lookup table. And suddenly you don't need such a crazy number down the bottom here. Just 0 will cause undefined. So min number here is meant to be 1. Basically, it's the same one here. It's basically the offset for the number there. So take say if you pass in number 0. 0 minus 1 is going to be out of range of that lookup table. You've got a different kind of UB there as far as violating the C++ standard contract goes, but it doesn't matter. It's all the same thing. The moment you passed in a value outside the range 1 to 26, you violated the contract. There was UB in the system, and arguing about what kind of UB or which contracts are now shredded as a result of this is a waste of time, really. Okay, so strategy. I mentioned game developers and Mars landers. So there's really four strategies that I sort of think of when I'm thinking how can we cater for developers. Trap enforcement strategy. That's the test user contract. We want all the not defining end debugs, so that when an assert fails, the program just bombs out. We just basically want to trap bugs. We want the program to not continue, because it's generally probably not a good idea to continue past the point where you know there is a bug in your program. You don't know what's going to happen, so it's probably not a good idea to continue. So non-enforcement strategy kind of means that's where the assert is just defines out to nothing. We're just going to sort of turn a blind eye to the fact that there's a bug here. Maybe it's more important that the program keeps running. Maybe we're just going to take that risk at runtime. Perhaps in a business critical system that is fairly simple, we perhaps sort of just ignore the fact that we know that we've got a bug. And I'm not going to say too much about that. I'm certainly not going to say much favorable about it. Closely related to it, there is a log and continue strategy, where you sort of struggle on, but not before trying to report that a bug happened. And really, if your program is exhibiting UB, you can't be certain that that report is ever going to make it anywhere anyway. But okay, fair enough. You're going to add it to a big long list that maybe gets reported back to a tester or headquarters, or gets added to a bug list. And I think typically that's just a list that will keep growing. The same as the list of warnings keeps growing in your build if you don't turn warnings into errors. And finally, prevention enforcement strategy. You first test your program thoroughly using the trap enforcement strategy. You exercise the test user contract as best as you can. You use all the tools available to you and all the testing regimes that are encouraged these days to test your code as thoroughly as possible and eliminate as many of the bugs as possible. And then you kind of basically reduce the risk down to an acceptable level. It's kind of yes, there is some risk associated with that, but whether or not you do that, you probably should always be trying to test using the trap enforcement strategy, no matter what other 3 of these you release your code as. And in some safety critical systems, you want to release your code with bugs being trapped. More on that later. So I've added a few columns to the list of useful flags that you can't see here. You know what? That may help a little. So now those 4 strategies: trap, non-enforcement, log and continue, and prevention are there as 4 columns. This shows where you might want to apply some of these compiler flags or toolchain flags, depending on what you're doing. So, for instance, if you are happy that you've prevented bugs, which you might want to do, say, if you're a game developer or you're writing some non-safety critical, performance critical code, you maybe test using trap enforcement, or but with optimization turned on. Sometimes sanitizers will find bugs only with the help of optimizers, interestingly. And also, you want to test with configuration as close to your release configuration as possible. But then you release with optimization still on, optionally still on, because you are confident if those bugs aren't there, it is safe to turn on your optimizer. For a lot of these things, though, 0, you would just keep the optimizer turned off. And you see there, a lot of these things are in the trap column. They are basically ways to ask your tool chain or your tools to tell you when there's a bug in the program. Okay. Again, there's a link you can find later on. Don't optimize until you sanitize is kind of the slogan I like to repeat from time to time. You test your code thoroughly before releasing it. Make sure that your tests cover the code as well as they possibly can. It can be difficult sometimes to get 100% coverage. You maybe can't get 100% coverage of a C++ program using unit tests alone, but you certainly can use automated tests to cover pretty much everything, maybe with a bit of help from mocks as well. And then even if your code coverage tool confirms that you're testing every function, every line, every branch of your software, there still may be conditions that are not caught. Like you might have tested a line, but you haven't tested a line with parameters at their extremes, where perhaps an overflow occurs. And this is where something like a fuzz testing utility can come in really handy. And so get your 9. So there's the notion of 9s in software reliability, where you want a server to be up all the time, and perhaps occasionally it does go down, or you need to upgrade it, and there's a moment where it's not running, so you don't have 100% reliability. But you maybe have 99.9% reliability, or 99.9999% reliability, and you can measure that, and you can strive to get closer to 100%, to the point where now this isn't the kind of huge concern that it might have been before. Here's my CMake from the code that I've been showing, and it's showing some of the flags that I'm using here. So for any build that I make, I turn on all those warnings. There's really very little reason not to ask your compiler to tell you about stuff going wrong and turn it into an error. There's a few flags sometimes. I've had to turn these off because GCC produces a lot of false positives. And then testing is it's not one of the 4 build types that you would get with CMake. You have debug, release with debug info, release optimized for size. When you run unit tests, none of those 4 really satisfy what you're trying to do there. Testing is some weird combination of optimization and turning on a lot of sanitize tools and bug trapping tools. So I actually add extra configurations above the basic 4 to CMake as I'm going along. And then, so I'm using CMake in conjunction with Conan, and the Conan command to configure CMake we see there is the Conan install command. your tool should have something similar. And here I can provide that file that I just showed you, the toolchain file, and then I say, use the build type test, not debug or release like you normally would. Use test there, and those particular flags will get turned on then. And I would kind of like it if more tool providers, people like CMake, ID developers, thought about adding extra build types like this, because debug is not actually what you want, really. And I mentioned, I'm not just talking about C++ today, in all software, if you can get things to fail when, when there's an error, that's a good thing. This is maybe not the best way to make sure that a bash script fails when there's an error, but let's say the Conan install command failed. If I didn't put that line 3 there, it would just carry on to the Conan build line potentially, which is, you don't want that. Fail fast, don't be helpful. So discussion is basically where I have an unlimited number of slides with typos in that I thought I may or may not get to. And I think we've got about 5 minutes. It's probably better if I just get, I'll just mention this paper that I read recently at Mars Code about the Discovery's lander software. It was written in C, but everything in there really applies to C++ too. That project used 4 static analyzers that they ran every day, plus a dynamic thread analysis tool, which sounds an awful lot like a forerunner to thread sanitizer. They turned on warnings when they built their software and turned those warnings into errors. They made sure, this is really interesting, that they had 2% of the code, at least 2%, and it ended up being a fair amount more than 2% of the code was assertions. I'm not sure if that was line numbers, perhaps. That's a lot of assertions. They were encouraging their developers to assert early and often in the code. And those asserts were not, they weren't sort of turned off or optimized out in their release build. If an assertion fired, halfway through the landing phase of the mission, there was a control program in the background. Yes, there was a full protection system was in place, which would detect that program had crashed with a non-zero exit, I would imagine, and went back to a safe state. And in a lot of safety critical software, particularly larger scale safety critical software, you want stuff to just, you don't want to continue past an error. You'd rather the program stopped really quickly and some other backup system comes into place. I've talked about sanitizers, and they are great at trapping bugs. But Clang Tidy and also Clang Static Analyzer, I've noticed they actually optimize around built-in unreachable. So when you're using built-in unreachable for optimization, you're basically saying, assume that this code path won't happen and optimize based on that assumption, and that can be incredibly powerful for optimizing. But unfortunately, there is at least 1 or 2 static analyzers out there that optimize analysis around the assumption that a bug won't happen. Yes, Tima. Okay, so the comment is very targeted use of built-in unreachable can improve performance, but just adding it to asserts, adding it to all your asserts, there's no evidence that that will improve performance. Okay, yes. Well, so that goes back to the choice that you make. Do you think there are bugs in your program? And I would say if you think there are bugs in your program, it's an unreasonable risk to optimize your code. And I know that is quite a hardline opinion to take.
I would say that every program has bugs. Almost every program in the world has bugs. So if you want to
right.
Increase the chance that it completely blows up.
Just from questions I've been asking at this conference, I'm not sure most software projects run automated testing. I'm not sure most software projects do unit testing. And if you don't do unit testing, you should have walked out of here 90 minutes ago and gone to a unit testing talk. I can't help you. I've got a few slides sort of where I rant about, what do you do if the quality of your code isn't good enough? None of this is any good if you're not, being really thorough about testing the code. And once you are, you will find that, no, your program isn't full of bugs. Particularly because with the sanitizer turned on, and it doesn't matter, yeah, you can call std terminate or you can call built-in unreachable with the sanitizer. They both do the same thing. You will have found nearly all of those bugs. You'd have got from 99 to 99.99999. And yes, I'd like to hear about the software system that does a good amount of testing and still has a lot of bugs in it. And yeah, yes, if you've got to basically make the choice. Do you want your code to go fast or do you want it to be safe? And yeah, you can dabble around and you can maybe turn on some sanitizer checks and optimize some other things. Or you can pick, okay, asserts, that's too big a risk for me. I don't want asserts to be unreachable, but maybe I want the C++, the stuff that's UB as of the standard to be optimized. But really, you're kind of humming in like you're neither one place or another. You're probably in a bad place either way already. You should either sort of commit fully to having your code correct and doing the things everybody should be doing anyway, regardless of all of this, or just like maybe think twice about turning your optimizer on at all, really. Yeah. But yeah, no, it's tough, and it's very easy for me to say, oh, this enormous legacy project with thousands of users shouldn't have bugs in it. But yeah, a lot of software out there is not in a good place, and yeah, maybe it shouldn't be optimized.